So we have seen the concepts or ideas of removal of pole at origin, removal of pole at infinity, as well as removal of pole at constant. Now let us see how to remove the conjugate imaginary poles, because it is a very good possibility to have imaginary poles for any given function because of the presence of inductors as well as capacitors in a circuit. Fine, we will see how to remove them. So okay, right, now if z of s is the given function, impedance contains pole on the imaginary axis at s is equal to plus or minus j omega 1, then z of s will have factors, of course, z s plus j omega 1 into s minus j omega 1, because they exist together, because they are complex conjugate, they cannot exist alone, right? Then it is going to become s square plus omega 1 square in the denominator polynomial, because we are considering them as poles, right? Okay, let us see now. Z of s is nothing but some p of s numerator divided by s square plus omega 1 square into q1 of s, let us say, just like that. Now we need to go for partial fraction expansion now in order to get the residues, or you have to separate the terms from this. So the only tool is or the main tool is partial fraction. Let us do that first. So since we have imaginary poles, and in conjugate we have k1 by s plus j omega 1 plus k1 star by s minus j omega 1 plus z2 of s. Let us say some term is there along with these residues. Okay, so for a positive real function, j omega axis poles must themselves be conjugate and must have equal positive and real residues. So this we have seen as a property of positive real function. So from that what you can say? From that you can say that k1 star is nothing but k1. You might have already solved many problems, you might have already observed this also, right? Now okay, then what happens to z of s? Z of s becomes, when k1 star is k1, it becomes 2k1 s by s square plus omega 1 square plus z2 of s, right? We can simply write like this just to avoid k1 star and all. Now okay, let us consider z1 of s as 2k1s by s square plus omega 1 square. Fine, then how we can write this? 1 by s by 2k1 plus omega 1 square by 2k1s. So just like this we can simplify it, right? So here I am considering it as ya plus yb because it is in the denominator, whereas it is z, and also it is 1 by something. So for z, when there is 1 by some new denominator, the denominator must be admittance. That's it. So that means ya is s by 2k1 and yb is omega 1 square by 2k1s, right? Then what is this? When this is admittance, it should be capacitor, right? It should be capacitor, and when this is admittance, this should be inductor. It is opposite to that of impedance, right? And what should be the value of capacitance? It is like cs, then c will be 1 by 2k1, it is like 1 by ls, then l is 2k1 by omega 1 square. Just simple comparison things we have to do, right? Okay, let us see how we can connect these things now. So okay, now we got the elements L and C. Okay, now what if that z of s is admittance y of s? So then this y1 of s will be this one, then you will get 1 by zA plus zB. In those cases inductor becomes, this capacitor becomes inductor here, and inductor becomes capacitor here, right? Very direct, because now we are assuming that y of s is given in place of z of s. So then we can just separate the imaginary poles with a parallel combination of L and C, right? And here if it is y of s, we can replace it with series combination of L and C. That is the only difference, because they are dual. You need to understand this particular thing, right? So this is how we are going to separate the imaginary poles, and they are going to become the L and C parallel combination if it is impedance, and L and C series combination if it is admittance. So these are the different ideas of synthesis. Okay, right, thank you.